Hello, we are the GIGASat Orbital team, and we are going to describe the orbital mechanics behind the hardware team's satellite. Hello, I am Colby Drabik. I'm a rising senior at Deering High School in Portland, Maine, and I intend to either be a chemical or aerospace engineer.
Hi, I'm Hannah Singer. I'm a rising senior from Ursuline Academy of Dallas, and I hope to become an engineer one day.
Hi, I'm Caitlin Waugh, and I am a rising junior at Trinity Classical Academy in Valencia, California, and I aspire to be an aerospace engineer.
Hello, my name is Samuel Cater. I'm a rising senior and I attend Broward College in South Florida. I intend to be an aerospace engineer in the future.
Hello, I'm Sofia Gallo, and I'm a rising senior at Scotch Plains Fairmont High School in Scotch Plains, New Jersey. I hope to pursue a career in aerospace engineering in the future.
When we set out on this mission, we aim to support the hardware team in their mission by crunching the numbers and figuring out how to efficiently get from low Earth orbit to geostationary orbit, an orbit that allows us to monitor one position of the Earth at all times. We did this by ensuring we met these 5 mission objectives. The first, delivery and positioning. And for delivery and positioning, we need to make sure that the payload makes its way from low Earth orbit to geostationary orbit, fulfilling the requirement to see one part of the Earth at all times. The next was orbital insertion. We need to calculate the engine burns needed to get us from low Earth orbit to geostationary orbit and make sure those were accurate and efficient. The next thing we need to do was we need to set up safe disposal and station keeping procedures. To ensure that the assets of us and others are protected in the dense region of geostationary orbit, we need to ensure that every move we make does not endanger our satellite or other companies' satellites, and we need to ensure that we act in a responsible manner in all maneuvers. We also need to meet the mission criteria to ensure that the satellite is in a position to collect and monitor crucial data from crucial areas and to satisfy the hardware team's operational requirements. Lastly, we need to ensure the longevity of the satellite. To ensure that our satellite works for a long time in the orbit we intend it to work in, we need to position it very accurately, so we cut down on the need of station keeping as much as we can, prolonging its lifetime. Here's our mission overview. We start in a build process and we eventually make our way to launch. From launch, we will launch into low Earth orbit. We'll perform what is called a Hohmann transfer, and people will explain this later. We perform that Hohmann transfer into geostationary orbit. We circularize the geostationary orbit. We commence observation. After about 10 to 20 years, we go from observation to end-of-life procedures, and we move our satellite into geograveyard. And as I said, people will explain these more in depth coming up. When we were looking at launchers to get our satellite into orbit, we considered multiple ones, including some foreign options such as the Ariane 5. We eventually settled upon the domestic Falcon 9 provided by Space Exploration Technologies, or SpaceX. They're an American company who launches out of Cape Canaveral in Florida, providing us an inclination of 28.5, easing the amount of plane change we need to do to get to our geostationary orbit. We chose the Falcon 9 for a variety of reasons. The Falcon 9 offers us the lowest cost to orbit and has one of the highest reliability streaks of any rocket. The only thing that can rival the Falcon 9 in terms of reliability is possibly the Russian Soyuz. With this elimination of a lot of risk, we can lower our insurance costs and have less worry when we choose to launch our satellite. The next reason is it has a low inclination at its launch. Falcon 9 launches from Cape Canaveral, and as I've said, that gives us a 28.5-degree inclination when we launch due east, allowing us to save some fuel during our plane changes compared to other options. Lastly, Falcon 9 offers an amazing cadence. They offer us the quickest boardroom to orbit time, allowing us to go directly from the build site to the launch site, as SpaceX launches at a rate of about 1 launch per every 10.1 days. Lastly, I want to talk about the launch site. We're launching from Launch Complex 39A, SpaceX's modern launch site, allowing easy access to our orbit. SpaceX is an industry leader, and they offer horizontal stacking and rollout, as well as support by our partners such as NASA and the United States Space Force to increase the synergy between the many operators of this mission.
This is the diagram of an elliptical orbit and the orbital elements that define its shape, its orientation, and the satellite's position in orbit. The apogee is the location in orbit where the spacecraft is the farthest away from the central body with the slowest velocity, while the perigee is the closest with the fastest velocity. The ascending node is the point in orbit which crosses the equator from south to north, while the descending node crosses from north to south. Similarly, the right ascension of the ascending node is the angle starting from the vernal equinox to the ascending node of the orbital plane. The argument of perigee is the angle from the ascending node to the point of perigee, while true anomaly is the direct location of the satellite in orbit measuring from the perigee. Inclination is the angle between the equatorial plane and the orbital plane, which determines the tilt of the spacecraft's orbit. Our satellite in specific is in a prograde orbit moving from east to west with an inclination of less than 90 degrees. However, GIGASat will not be in an elliptical orbit because, since it is in geostationary orbit, it will have an eccentricity of nearly 0, where this determines the shape of the orbit, making it more circular.
After the spacecraft is launched, it is placed into a low Earth orbit, which we call a LEO, and can also be called a parking orbit. A LEO is a nearly circular orbit. GIGASat's altitude is roughly 265 kilometers above the Earth's surface, and it has a period of 90 minutes. The semi-major axis, or the radius, of GIGASat's LEO is 6,643 kilometers, as shown by the yellow line. While in this orbit, the satellite will move at a constant velocity of 7.746 kilometers per second. Additionally, we will place the satellite at 70 degrees west. This translates to 290 degrees east. In the image, 70 degrees west is the pink dot near Ecuador and Colombia, and the satellite's field of view is the yellow round. With this field of view, the GIGASat can monitor wildfires, oil spills, and more. This is the LEO ground track. A ground track is the path on the surface of the Earth directly below the spacecraft. It is a set of points at which the satellite will pass overhead. The Earth rotates at 15 degrees per hour, so every 90-minute orbit, the Earth rotates 22.5 degrees underneath the spacecraft. If you look at the graph, one node to the next node, or one equator crossing to the next, is 22.5 degrees and is equal to one 90-minute period. This ground track shows the satellite's first 5 orbits. The purple dot is the first ascending node at 5 degrees. This is the first time the satellite crosses the equator after launch. A descending node is when a spacecraft crosses the equator going north to south, and if you look at the graph from left to right, you can see that it descends as it crosses the equator. Additionally, the Earth has a non-spherical shape, and it bulges at the equator, and it is this bulging that causes the line to move slightly to the west with each subsequent orbit. GIGASat's mission cannot be conducted from LEO, however. The satellite needs to be transferred to its geostationary orbit. So we use a Hohmann transfer, which is an elliptical transfer orbit used to maneuver the satellite from LEO to its geostationary orbit, GEO. A Hohmann transfer consists of 2 burns, one to get the spacecraft out of LEO and one to get the spacecraft into GEO. A burn is the turning on of a rocket or the burning of propellant to change the velocity of the spacecraft assembly so that it can escape its current orbit and maneuver into another one. After the first burn, the satellite will coast uphill in an elliptical orbit, which is shown in red in the moving image and green in the hand-drawn image. The spacecraft will only travel on one half of the elliptical orbit, 180 degrees. This is the same LEO ground track, but this one highlights the last 2 to 3 orbits before the first burn of the Hohmann transfer. If you look at that small line on the far left, imagine that it stretches to the equator. That crossing of the equator is an ascending node and is roughly the location that initiates the Hohmann transfer, 189 degrees east. Where did that 189-degree longitude come from? Well, the Hohmann transfer spans about 100 degrees from burn 1 to burn 2. We want burn 2 to occur at the target longitude of 290 degrees east, so the first burn needs to be 101 degrees west of that, which is 189.
The first burn will start off our journey from LEO to GEO. We can recall that a burn refers to the event of turning on a rocket to change the velocity of the spacecraft assembly. At burn 1, it is at stage 2 of Falcon 9. After about 21 hours, the GIGASat will make 15 revolutions around the Earth, and the satellite will thrust as it crosses the equator. This chart gives the ascending nodes and descending nodes as well as the NET at each revolution. An ascending node is when the spacecraft crosses the equator on the way from south to north, and a descending node is when the spacecraft crosses the equator on the way from north to south. The NET is the time from the first node starting from 0 to about 22.5 hours. The spacecraft first crosses the equator at a descending node of 5 degrees, and at this point, the satellite will begin its first burn at the ascending node, which has a longitude of 189 degrees. The GIGASat ends its 15th revolution and fires the rocket with this longitude. With an inclination of 28.5 degrees, the GIGASat will start its transfer orbit to reach GEO orbit. The transfer orbit takes about 5 hours and 16 minutes. During this stage, the rocket attached to the satellite will be dropped and will go back down and burn up in the atmosphere. This is called a retrograde burn. A retrograde burn is one that subtracts from the ship's orbital speed. We don't want to have to accelerate all that extra mass. Since the speed of LEO orbit is around 7.75 kilometers per second, GIGASat will thrust up to a speed of 10.2 kilometers per second, coast uphill, and enter an elliptical orbit at the perigee. Therefore, the delta V is 2.46 kilometers per second. The satellite will travel 180 degrees and reach the apogee, where it will then make the second burn. These ground tracks show the transfer orbit. The left end of the data shows the first burn at 189 degrees. As the satellite starts its elliptical orbit, we can follow the tracks at a constant speed, since the satellite is traveling faster than the Earth. The Earth turns underneath the satellite at a constant speed, but the satellite slows down as it coasts uphill from 180 degrees as we go from perigee to apogee. Because the spacecraft has a slow velocity, the Earth's constant speed moves faster than it, and the spacecraft backtracks relative to the Earth. Therefore, on the ground tracks, the GIGASat traveled 180 degrees, yet at the far right point at the end of the data, it backtracks 71 degrees. So the satellite really only traveled 109 degrees on the graph from point to point. At geo altitude, again as we cross the equator, GIGASat executes its second thrust to enter geo. Burn 2 will occur at the apogee, and at this point, the satellite will be traveling at speeds of 1.6 kilometers per second. When the second thrust is made, the spacecraft will travel at speeds of 3.07 kilometers per second in order to stay in geo orbit. The delta V is 1.8 kilometers per second. It is important to note that each of our two thrust events include a part of the required 28.5 degree plane change maneuver. This means that these thrusts are not in the plane of the current orbit. In geo, over our target longitude, we orbit in geo for the satellite useful lifetime of about 10 years.
This is a diagram of the equatorial plane, labeled in green, and the orbital plane, labeled in red. This is the second burn, where there is a 26.3 degree plane change in order to relocate to the equatorial plane, where the geostationary orbit will be. VC2, which is 3.07 kilometers per second, represents the circular velocity of the satellite on the orbital plane, and VT2, which is 1.6 kilometers per second, represents the transfer velocity to the equatorial plane. Using the law of cosines, we found the rate of change in velocity between the two vectors, which was 1.78 kilometers per second, allowing us to understand how fast the transition between both planes is. After this, the satellite will be in geostationary orbit, where it will be capable of performing its functions properly in the most efficient location. However, once securely in orbit, that does not mean that the work is over. Since the Earth is not a perfect sphere, as the north and south poles are flatter due to its rotation, the orbit is not completely steady, as the satellite may begin to drift to the west. For this satellite in geostationary orbit, the drift rate will be around 2 meters per second per year, which is the delta V. Delta V is the change in velocity, otherwise known as acceleration. Though there is no atmospheric drag, since a geostationary orbit is too far away from Earth in comparison to a low Earth orbit, solar winds, which are streams of particles released from the sun, collide with the satellite and impact its position and function. In order to correct this, thrust is needed to put GIGASat back into its correct location in orbit.
300 kilometers higher than that of a geostationary orbit. Geograveyard orbits are used to reduce the amount of space debris found in Earth orbit, which reduces the chances of collisions in Earth orbit. Geograveyard is used in accordance with regulations set by the Interagency Space Debris Constellation Committee. Geograveyard could prove to be a vital resource once we find a way to access the equipment on the decommissioned satellites. GIGASat has a planned lifetime of about 10 years. Once these 10 years have passed, GIGASat will be transferred from a geostationary orbit to a geograveyard orbit to comply with space laws. GIGASat will be relocated using a Hohmann transfer. We will initiate the transfer once the overall mass of GIGASat reaches 820 kilograms. The transfer will use two burns that will use two separate solid rocket boosters located on opposing sides of the GIGASat. The two burns surpass the minimum delta V of 11 meters a second required to transfer to geograveyard. After the transfer, the GIGASat will be decommissioned indefinitely or until we find a way to retrieve the equipment aboard the satellite. So, in conclusion, we'll be launching GIGASat from Cape Canaveral aboard the Falcon 9 rocket. GIGASat will enter low Earth orbit, and after approximately 22 hours, it will be transferred to a geostationary orbit over 70 west using Hohmann transfer, including a plane change. GIGASat commences monitoring of vital environmental factors for a period of 10 years before being decommissioned and transferred to geograveyard. However, we wouldn't have been able to complete this project without everyone at SEAS, which brings us to the conclusion of our...
We would now like to take some time to talk about what SEAS has meant to us. For me, SEAS has meant a lot to me. SEAS has allowed me to further my collaboration skills as I worked with a team to design the concept of a satellite, something I thought I would never do. SEAS has also allowed me to further focus what my career path is going to be. Furthermore, I have also made connections with people who have the same interests as me, and I hope these connections grow into lifelong friendships. Lastly, SEAS has allowed me to gain further experience in a high workload environment and study under an experienced professional.
I appreciate SEAS because it allowed me to explore working in a team further as well as developing my teamwork and time management skills. SEAS also allowed me to develop connections with like-minded individuals who shared my passion for STEM and aerospace engineering.
SEAS has helped me step out of my comfort zone back at home and immerse myself in new STEM experiences. I met many new people who share my interests, and I learned of new paths to take to achieve my future goals and then some. I thank SEAS for allowing me to, for the first time, work on a realistic and creative project that helped build upon my knowledge of aerospace engineering.
I am so thankful that I had the opportunity to be a SEAS intern. What I have learned and the relationships I have built truly make this program special. I have met the most wonderful and hardworking staff, mentors, and peers here, and I will never forget the memories I have made with my team. SEAS only furthered my interest in aerospace engineering and gave me a taste of what I could accomplish if I worked hard towards my dreams.
SEAS, I was able to apply my knowledge to something greater than myself in an uplifting environment where I was encouraged to make mistakes and try again. SEAS solidified my hope to become an engineer one day, and I am grateful for the people I met and the experience I gained during my time here. As a whole, we would like to thank SEAS, NASA, and the Texas Space Grant Consortium for inspiring us to further our career in education and expand our connections in the STEM field. We would also like to thank the University of Texas and the Center for Space Research for providing their facilities, knowledge, and encouragement through the duration of our internships. And finally, on behalf of the entire SO2 team, we would like to thank Dr. Fowler, our mentor, for everything he did for us. We admire his passion and dedication to both STEM and our project, and we could not have done this without him. So thank you, Dr. Fowler, for guiding us through our project, imparting us with your wisdom, and furthering our education in the STEM field. These are all of our citations, and thank you for attending our presentation.